Consider this tree. So today we will be talking about AVL trees deletion. Remember this table. I'll tell you the importance of this table in a while. So at present, consider this example. This is the given AVL tree. So first let us look at what are the balancing factors of each and every node and check whether the tree is balanced or not. So the balancing factor here is 0. Okay, because you don't have left side, you don't have any levels on the left hand side and you don't have any levels on the right hand side. So here it is also 0. All the leaf nodes will be having the balancing factor as 0 for us. Now consider the balancing factor of this node. You have only one level below it and you have 0 levels below it. So usually the balancing factor is calculated as height of the left subtree minus height of the right subtree. So balancing factor is usually calculated as height of the left subtree minus height of the right subtree. So here what is the height? You have only one level, means the height of the left subtree is 1. Here you don't have any level, so height of the right subtree is 0 for you. So 1 minus 0 is 1. Then here you have one level on the left hand side, one level on the right hand side. 1 minus 1 is 0 for you. Now you have for this node you have two levels on the left hand side, you have two levels on the right hand side. So here the balancing factor is also 0. Now calculate this. So you have 0 levels on the left hand side for this node, you have one level for the right hand side of this node. So 0 minus 1 is minus 1 for us. Here it is 1 minus 1, it is 0. So for this node you have two levels on the left hand side and you have two levels on the right hand side. So 2 minus 2 is 0. For this node, for root node, you have 1, 2, 3 levels below it on the left hand side. Here you have 3 levels below it on the right hand side. 3 minus 3 is 0. So in AVL trees, as long as the balancing factor is either 0, 1 or minus 1, we don't have any problem. That is, tree is balanced for us. So all the nodes should either have 0 or should have 1 or should have minus 1 as the balancing factor. If you have any other value apart from that, the tree is imbalanced for us. Now consider, let us try to delete some elements and see if you get any balancing factor, any values apart from this, and how do you balance it. Let us go around it. So let us assume, so you want to delete following elements. So let us assume first you want to delete element 2 from this tree. So after deletion you have to recalculate, after deletion of each and every node you have to recalculate the balancing factors of every node. So you want to delete 2. So once you delete the element 2, so calculate the balancing factor here. So here the balancing factor will be 0 for you, because you don't have any nodes on the left and right hand side after deletion of 2. What will be the balancing factor here? So one level, and here you will have two levels. So the balancing factor here will be 1 minus 2 is minus 1 for us. What will be balancing factor for this node? Do you have any change here? So how many levels do we have here? 1, 2, 3. You have 3 levels. Here how many levels you have? 1, 2, 3. So there is no balancing, there is no change in balancing factor here for you. Now consider, now you want to delete the element 3. So delete the element 3. Now calculate the balancing factor here. So you start calculating the balancing factor right from the point where you have deleted the node. Now, so the balancing factor here of these 3 nodes will be same for you, because we have not done any modifications here. Now the balancing factor changes here. That is, here you have 0 levels, here you have 2 levels. So 0 minus 2 will be for you. So you have 0 levels. Here you have 2 levels. So 0 minus 2 will be minus 2. Okay, so this is your new balancing factor for this node. So we have got a balancing factor as minus 2. So as long as we have 0, 1 and minus 1, tree is balanced. But if you have minus 2 as the balancing factor, then the tree is imbalanced for you. So you have to balance this tree based on the table which is given here. So for this table, for this node, so at this point you have got the imbalance. What was the previous balancing factor for this node? It was minus 1. Okay, previous, before getting minus 2 it was minus 1. And to this node, on the which side we have deleted the element which has caused the imbalance? On the left hand side. That is, you deleted 3, then only you got minus 2, then 3 got imbalanced. Before that 3 was balanced for us. So deleting a node on the left hand side has caused the imbalance for you. Okay, so you write L. So it is L minus 1. That is, what you have done is you are deleting a node from the left hand side, and before deletion what was the balancing factor of this node? It was minus 1. So after deletion it got unbalanced for you. So what is L minus 1 for us? It is RR. So with respect to this node you have to apply RR rotation. So with respect to this, if you apply RR rotation means you will be having R. So whenever you have RR rotation, what you do is you pull the element between both the R's. So let us see how it happens. So the previous tree which was given to us was 14, 4, 3, 9, 7, 10, 21, 15, 18, 28, 26, 8. So here the balancing factor was minus 1. After deletion it became minus 2 for us. So then we said that we are deleting the node on the left hand side. Previous balancing factor was minus 1. So L minus 1 means L minus 1 is RR for us. So you have to apply RR rotation with respect to the imbalanced node. So this is the imbalanced node. With respect to this you apply RR rotation. You pull the element between both the R's. So if you do that, resultant tree will be, so if you pull the 9 above, what happens is 9 becomes root, 4 comes down to the left hand side, and here you have the element 10. But previously what was the left hand side element for you, for the 9? It was 7. This is occupied by the element called as 4. So what you do is 7 is greater than 4 with so previously this was the place of 7. So now at this point 4 has occupied it. Now what you do is you compare 7 with 4. 7 is greater than 4, so 7 will be placed onto the right hand side of 4. So this is your new balanced tree. So this is a new balanced tree with the balancing factors as 0. For this it is minus 1, 0, 2 minus 1 is 1 for us. So minus 1, 0, 0, 0, 0 and 0. So the tree is balanced for us. Now we want to delete the element 10. So element 10 has to be deleted. So if you delete the element 10, what will be the balancing factor? Let us calculate. So if you delete the 10, the balancing factor here will be 2 for you. Okay. So previous now here let us calculate what we have. What is the type of rotation which we have to apply. So with respect to this node, the imbalance has occurred here. So for with respect to this node, you are deleting an element on the right hand side. So for this node, what was the previous balancing factor for you? R1. So what does R1 mean? So R1 means LL rotation. So R1 means LL. So with respect to this node we have to apply LL rotations. So you say that so you apply LL rotation. This is a null node for you. So if you look at this case, if you only look at this tree here, subtree, so you have 9, you have 4 and you have 7. Whenever you have this sort of cases, you don't have to again go through the process of applying LL and those kind of things. You simply apply the same rule, that is you have A, B and C. So you directly place the element in this order. So whenever this set of cases apply, directly say that C always becomes the root and out of AB whichever is smaller becomes the left hand side part, and whichever is bigger becomes the right hand side part. So this gets attached to your root node. So this is your resultant tree. So this will be attached to your root node. So the resultant tree will be of this form. So we will be having 14, 7, 4, 9, 21, 15, 18, 28, 26 and 30. So calculate the balancing factors: 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 2 minus 3 is minus 1 for us. Okay, so now let us delete the element 18. So if you delete the element 18, there is no modification to the tree. Okay, tree will be balanced for you. Next, try to delete element 49. Okay, so sorry, not 49, let us delete element 4, then we delete element 9. So delete the element 4. You don't have any modifications to your tree because the tree will be balanced for you. But only thing is, after deletion of 8, the balancing factor of this becomes 0. After deleting 4, the balancing factor of this becomes minus 1. But all the other nodes remains the same for us. Next, delete element 9. If you delete the element 9, the balancing factor of this becomes 0. And balancing factor of this element becomes, so here you have 1, 2, 1, 2 and 3. You have 3 levels on the left and right hand side. You have only 1 level on the right hand side. So 1 minus 3 is minus 2 for you. Okay, that is your dealing. So you have got an imbalance. So for this, with respect to this node, you have deleted the element on the left hand side. And what was its previous balancing factor for us? L minus 1. So what is L minus 1? So L minus 1 is RR for us. So with respect to this node, you apply RR rotation. When you have RR rotation, you pull the element between both the R's. So 21 becomes the root, right hand side will be same for you. So if 21 comes up, so what happens is 14 falls onto the left hand side. So 14 falls onto the, 40 falls onto the left hand side, and we have the element, so to 14 we also have the element called as 7 which is attached to it. So everything falls onto the left hand side, but previously the left hand side of 21 was 15. Now it is occupied by 14 here. So what you do is you just compare 15 with the element 14. 15 is greater than 14, so 15 comes onto the right hand side. So the tree is balanced for us. So balancing factor is 0, 0, 0, 0, 0, 0 and 0. So the tree is balanced for us. Now try to delete element 14. So when you want to delete an element 14, you have to replace it with the appropriate element. So we have two ways in which you delete an element from a binary search tree. That is, whenever you have to delete something here, you follow the same rule as binary search tree. That is, if you want to delete anything which is not a leaf node. Okay, so this is the process, which same process as a BST has to be followed. Suppose if you want to delete 14, jump to the left and find the maximum element. That is what you do, right? So you jump to the left and find the maximum element. You don't have an element, so 7 is the maximum element on the left hand side for you. You replace 14 with 7. So the resultant tree will be 21, 7, 14, 15, 28, 26, 30, and then you delete element 14. So you swap it. So the resultant tree will be a balanced tree for you. So here you have 0, minus 1, 0, 0, 0, 0. Next, delete the element 7. If you delete the element 7, so 15 gets attached to 21. So that is the process. So you will be having 21, 15. So you have 28, 26, 30. Next, you delete element 15 here. First, before deleting element, calculate the balancing factor 0, 0, 0, 0, and this is 1 level, minus 2 you have minus 1. So if you delete here the element, so here you will be having the, once you delete 15, the balancing factor of 21 becomes -2 for us. So you are deleting with respect to this node where the imbalance has occurred. You are deleted element on the left hand side, and what was the previous balancing factor for it? -1. So L minus 1, so L minus 1 is RR for us. So with respect to this node, you apply RR notation. Whenever you have RR, pull the element between both the R's. So the resultant tree will be 28, 30 will be same for you. So 21 falls onto the left hand side, so 21 comes here. Previously this place was occupied by 26, so you compare 21 and 26, so 26 greater than 21, so 26 comes here. So this is your resultant tree. So here the balancing factor will be 0, -1, 0, 2 minus 1 is 1. So this is a balanced tree which you have got. So this is the process of AVL deletion. So for all these things you have to by heart and remember this table, which is important. If you remember this table, everything will fall into pieces for you.